Hi everyone, I'm Zhihong Zhu. Today I'm going to talk about how to perform MT-Kojo. In observational studies, we can directly measure relationships between traits. For example, people with schizophrenia have low levels of vitamin D, which has led to hypothesis that low vitamin D is a risk factor for psychiatric disorders. But this is very difficult to test. Mendelian randomization provides a way to test for causality using GWAS results from the putatively causal trait and from the outcome. However, in testing these relationships, we may wish to account for other confounding factors. If we had individual level data, we could account for confounding factors through their inclusion as covariates. MT-Kojo is a method that allows us to condition on confounding factors when we only have GWAS summary statistics. The conditional GWAS allow us to investigate causal relationships free from the bias of confounding factors. As I mentioned, accounting for confounding factors can be achieved by their inclusion as covariates. Due to the stringent assumptions of Mendelian randomization methods, it is not straightforward to fit genetic variables jointly. Instead, we can achieve our goal by a two-step approach. The first step is to adjust both focal trait and risk factor for covariates. And the second step is to investigate the causality. The estimated causal relationship is then free of confounding with covariates. The MT-Kojo estimates causal effects of covariates on focal trait and risk factor, and then perform conditional GWAS on those traits. The MT-Kojo method uses GWAS summary stats, which can be either from a single cohort or multiple studies. Let me talk about some details of MT-Kojo. The first step of MT-Kojo is to estimate the causal effects of covariates on focal trait and risk factor. This step is conducted by GSMR, a Mendelian randomization method, which has similar concept to randomized control trial, the gold standard to test for causality. The GSMR method uses SNPs as instruments to test the causal effect, taking the correlation between SNPs into account. Paratropic SNPs for two traits commonly affect estimates of causal relationship between two traits. The highly outline excludes those paratropic SNPs, which have effect sizes that deviate the relationship at causal SNPs. The GSMR method with highly outline investigate the causality, and the causal effect is unbiased in the presence of non-genetic factors. Because of this, the MT-Kojo result is free of bias. The GSMR method uses multiple SNP instruments. Therefore, we need to incorporate the correlation between SNPs. So we need a cohort with individual level data to provide an LD reference. The second step of MT-Kojo is to conduct the conditional GWAS. We derived the formula to estimate the conditional effects. As shown in the equation, the effects of SNPs are directly from GWAS studies. The MT-Kojo effects also needs estimates from LD score regression analysis. Due to the limited time I will not describe the details here. We compare the MT-Kojo result to the traditional method if we have individual level data. The two results are identical. Furthermore, MT-Kojo accounts for distinct sample sizes and overlapping individuals when there are multiple GWAS studies. Lastly, the MT-Kojo method is free from bias. I will talk about it in detail. The MT-Kojo method is free of bias. There are two sources of bias, environmental and genetic factors. Suppose a covariate does not have a direct effect on focal trait. We may still be able to observe association between covariates and focal traits because of non-genetic and genetic factors. So when we perform GWAS of focal trait conditional on covariates with observed data, we are likely to detect superior GWAS hits. MT-Kojo can address these issues. Firstly, MT-Kojo can unbiasedly estimate the effect of covariates on focal traits in the presence of non-genetic factors. Secondly, because of the causal effect, MT-Kojo is free of pleiotropic effects. In general, the MT-Kojo method is free of bias. The MT-Kojo method has been implemented in software, free to download and easy to use. The MT-Kojo software only needs GWAS summary stats. The command of MT-Kojo is very simple. Press enter and the analysis will be finished in few minutes. This is the link to MT-Kojo web page. When you open the page, you can easily find the command. To perform the MT-Kojo analysis, we need GWAS summary stats, LD reference sample, and LD scores. Today, I will use the GWAS of vitamin D conditional BMI as an example. In this example, firstly, we will need the original GWASs of vitamin D and BMI. The GWAS summary stats are in MT-Kojo format. There are 8 columns in the MT-Kojo format file. The first row is the header. The MT-Kojo will use the SNP ID column to match the GWAS datasets with the LD reference. The SNPs which are not matched will be excluded. The allele frequency is the one of the effect allele A1. Likewise, the effect of SNP beta is that of the effect allele A1. So please double check the SNP ID A1, A2, allele frequency, and beta before performing your MT-Kojo analysis. Secondly, we need an LD reference sample. If we have the cohorts where we perform the GWAS, we can simply use the subset of the GWAS cohort as LD reference. Usually, the GWAS cohort is not available. So we need a cohort of the same ancestry as the GWAS cohort. We recommend using a relatively large cohort. When the LD reference sample is large, the LDs in the LD reference are likely to be consistent with the GWAS cohort. In the demonstration, we will use a cohort with 10,000 individuals as the LD reference. The genotypes of the LD reference sample are saved in p-link binary format. Thirdly, we will download the LD scores from LD score GitHub. Now, let's perform the MT-Kojo analysis of vitamin D together. We will download the software and the datasets used in the analysis, the GCTA software, the GWAS summary stats of the focal trait vitamin D, and the covariate trait BMI. The LD reference sample, and LD scores. When all the datasets are ready, we can perform the MT-Kojo analysis of vitamin D. Now the datasets are ready. Let's have a look. This is the original GWAS of vitamin D in MT-Kojo format. This is GWAS of BMI in MT-Kojo format. We create a list of GWAS summary stats for the MT-Kojo analysis. The first row is the focal trait vitamin D. The rest rows are the covariates. We only have a single covariate BMI. If there are multiple covariates, you can simply add them into the list. This is the LD reference sample in p-link binary format. These are the LD scores for 22 chromosomes. The LD scores are downloaded from LD Score GitHub. When all the datasets are ready, we can perform the MT-Kojo analysis. The command is very simple. Copy the command and press enter. Then the MT-Kojo analysis starts. Now the MT-Kojo analysis is finished. It is very quick, only around 3 minutes. The MT-Kojo analysis uses the causal effect of BMI on vitamin D. The estimated causal effect is free of bias. Therefore, it is less likely that the MT-Kojo caused the spurious conditional GWAS hit. Let's have a look at the MT-Kojo result. The .mtCOJO.cma file contains the original GWAS estimate of vitamin D and the GWAS estimates as adjusted for BMI. The first 8 columns are the original GWAS estimates. And the last 3 columns are the GWAS estimates of vitamin D adjusted for BMI. We plot the conditional GWAS result of vitamin D. There are more than 100 significant loci in the conditional GWAS. Those loci are vitamin D specific, free of confounding with BMI. Likewise, we performed the MT-Kojo analysis for schizophrenia conditional BMI, and then conducted the GSMR analysis to test for causality. Conditional on BMI, the association between vitamin D and schizophrenia remains significant. Take-home messages. MT-Kojo has easy-to-use software and just a simple command and pressing enter. It only uses GWAS summary stats, and the MT-Kojo method is free of bias. These are the references of MT-Kojo analysis in the demonstration. I would like to thank my supervisors, Naomi, Peter, and Jen, who supervised me and helped me with tasks. I would also thank Joanna, Naomi, and John, who offered me the great example of MT-Kojo analysis. Finally, I will give special acknowledgement to all PCTG group members and all the co-authors who worked on those projects. Thanks for your watching.